What happens when an output buffer becomes full? Let's wait until we write it out to persistent storage, which even with SSD takes a little while. While that's going on, twiddling our thumbs, contemplating our navels, there's a wonderful word, amphilosis, which means contemplating your navel. See if you can use it in conversation today. Sitting around and doing nothing while you're waiting for the output to output is a really bad idea. What about when I run out of things from input 2? I have one buffer in memory for input 2. I have run out of everything from input 2, but I can't go ahead and do something with my other inputs because the values, the next block of input 2 might be the next smallest. More amphilosis. See, you can use it in conversation easily. You're twiddling your thumbs, you're waiting until that input comes in. That's really bad. So what you could do is you could go ahead and read in a bunch of pages so that you're always ahead of the game. You have more than one page for each input file, and you have more than one page for each output file. So for example, suppose that I have 2 pages for my output file. Could be more, let's just deal with 2. So I have a second page for my output file. My first output buffer gets filled in, my first buffer output page. What do? I write it out. In the meantime, the world doesn't stop. No amphilosis. You got another page. You put stuff in that page. So there's other work going on interspersed with you doing that right. What about the input files? If I have 2 or more pages from my input file, from each input file, I run out of room from one of them, I still got another. I can keep doing my work. What I'll do is I'll read in a second page. I'll bounce back and forth. I'll read into this, I'll use this page, it's empty. I'll read something new into that. In the meantime, I'll use the other page. So I always have a shadow page in reserve so that I never have to wait for I/O, assuming, of course, that I can read in the next page before I use up the page that's there. I can do the same thing, not just with 2, but with 3. So basically, this is kind of similar to the same thing as having bigger pages, but the advantage is I can read extra stuff into a separate page. So it's a little bit different from having a bigger page. I could work with 1 meg pages, but then if I'm reading in another whole 1 meg page, I'm overwriting stuff that I haven't used yet. So maybe I have, instead of having a 1 meg page, I have 10 things that are 100K or something like that. But there are trade-offs in this. Now, again, having larger pages or larger number of pages for each file means that the fan out, that B-1 that we use for merging, that gets worse. So having more pages for each input file means I don't have to wait, but it also means that my ability to merge together B-1 things has been reduced, let's say by half. So if what I do is I devote half of my buffer pages to being shadows so that I don't have to wait for I/O. I don't have to wait for I don't have to wait for O, either one. But now, instead of having log to the base B-1, I have log to the base B-1 over 2. Got the idea? So it makes the I/O better. In practice, most files can still be sorted in 2 or 3 passes. So this double buffering idea is really simple. I've already explained what's going on. So what you do is you have information that's read inside these shadow blocks. So you've got purple and yellow blocks, wonderful colors. Hard to see the block on the purple, but it's there. Basically, you have, for input 1, you're going to have 2 blocks. And if you run out of the yellow, you still got purple. And while you're processing purple, you read in the next thing into the yellow block. So you start off with blocks 1 and 2 in yellow and purple. When you're done with yellow, you still have the second thing from input 1 inside the purple. And while you're processing it, you're reading in a new yellow block, which would be the block 3 in the first input. Same thing for all the things up to whatever your value of K is. Input K, you got 2 blocks for it. One of them gets used up, you use the other. You just bounce back and forth, which is current and which is in reserve. And when one runs out, you just read in the next. And now on the output, you're doing exactly the same gimmick. You've got 2 blocks. When one of them becomes full, you don't go into amphilosis mode, technical term. You don't go into amphilosis mode, amphilytic mode, I don't know. Instead, what you do is you write out that block and you've got another place to put new things. And you can do the same thing if I/O takes a long time, where you have, instead of just 2, you can have 3. But remember the trade-off. Life is full of trade-offs. If you have more blocks to try to prevent having to wait, then your fan-out gets worse. Because what you're doing is you're merging, instead of B-1 things, you're merging B-1 over 2 things in the diagram shown, or B-1 divided by, T, or whatever the value is. So that's the general idea of what's going on. Still 2 to 3 things. And here's the interesting thing about sorting, and this is yet another wonderful thing that Jim Gray, whom I've mentioned a whole bunch of different times, is responsible for. Basically, Jim, 30 years ago, more, 35 years ago, he produced something which was called minute sort, which is how much data can you sort in a minute? And then it also became, how much data can you sort for a penny? Due to inflation, this is now called 10-cent sort. There was also, more recent, something called joule sort. How little energy can you use to sort 10 to the 10th records? What's the smallest amount of energy you can use to sort 10 to the 10th records? Seriously, I am not joking. And there is huge stuff that goes on. I mean, in the 1990s, there was something 1 million records of size 100 bytes, and typically could do it in 15 minutes. The world record was 3.5 seconds with a special purpose algorithm. I'm about to show you a website that talks about Daytona and Indy, and I'll give you a pointer to that website. The website is right there, sortbenchmark.org. What does Daytona mean? You have to go ahead and have a standard algorithm that is part of ship code that is not specialized just for this sort of benchmark. What does Indy mean? You can have specialized sports cars, especially for that. I didn't make up the names, they're not my fault. Not every bad joke is my fault. So that's the general idea of what's going on. And there were early benchmarks which have actually changed. There was the original thing, terabytes per minute you can sort. There is something more recent, which is called a cloud sort, that I'll give you a pointer to recent results on. Minisort, joule sort. It was penny sort. Now it's the 10-cent sort. There was a terabyte sort, which ended up disappearing because over time it became too equivalent to other stuff. But let me go ahead, because I am almost done, and I actually will probably be able to start on the next lecture, even though I haven't posted it. But I want to show you a website. And I also will give you a pointer to 3 interesting, relatively recent papers. This, of course, assumes that I can switch over to my browser, which okay, too many windows, as usual. Always. You would be amazed. No? Okay. I will just take something else, and I will just go to the website out of something else. So this is a website. Typically have 3 browsers open with huge numbers of windows. But this is just sortbenchmark.org, and every year there's a group that looks over results that are submitted for each of these sorting algorithms. In particular, there are 4 that are out there. There's a 10-cent sort. There's something, and I'll tell you what that is. It's got an acronym that it took me a little while to figure out what it was. There's something called NAT sort, and there's 10-cent sort, and there's NTO sort. NAT sort is a cloud algorithm that actually uses Apache Spark. And 10-cent sort, I've told you about how much sorting in using 10 cents. And NTO sort is a variation of joule sort. And if somebody can figure out what the NTO stands for, please let me know, because I don't know. And you've got the Daytona and the Indy. And you have the records about how much can be done. And the things describe how much is done. And each of these things is clickable to be able to get more information. So again, Daytona is running standard sorts of stuff, and Indy is running something specialized just to be able to make this algorithm work. Of course, variations of all these things exist inside database systems and other data management systems. So it's kind of cool to see what the results are. And they keep changing over the year. The 2019 things are going to come out based on submissions in September of 2019. And people care about this because they get to be able to boast about what their database system can do. Academics get to boast about what they've achieved, and management systems boast, we can do better than these other guys, we win. And when that slide says that this has become a blood sport, believe me, and I won't bother, actually going into full mode on this, this is gonna be good enough. But there really was a blood sport where people were competing commercially like crazy based on this stuff. And, this guy isn't doing it right, check it out, et cetera. And this is special code that he put in just to run the benchmark, and it doesn't really get shipped, and it requires too many knobs. This is money. And people went crazy over it because it's a way of boasting that we're better than the other guy. Hardware guys would run these benchmarks with their choice of database system to boast about their hardware. Database management systems would boast. Networking people would say, use our stuff. All kinds of huge stuff going on in this, and it was a big deal. So to say that this was a blood sport is true. Sounds silly, but when it comes to money, it is true. There are, well, I guess I will switch over. There are 3 more recent papers that I will point you to, and there are other versions of it, but 2011, a group at UC San Diego, the guy who ran it is currently at Google. They did something called tritone sort, and they wrote a published paper about the details of it, which I point to up here. And it's worth looking at about how you can use fast networking and large distributed systems to be able to get really, really impressive sorting capabilities. This is kind of a coda. If there are people who want to discuss these papers, give me a day's warning, and I will be happy during office hours or a special meeting to discuss any of these things with you to the extent that I know about them. This is a paper, it is a great paper if you want to understand relatively modern sorting, see what's going on there. But that's 2011. Then there was work that was done for something called NADSort. I can tell you where the NAD comes from. It stands for Nanjing University Alibaba Group and Databricks, NAD. So they called it NADSort, and it's a cloud sorting algorithm taking advantage of Apache Spark. Apache Spark is something that was originally developed at Berkeley. Databricks is a company that commercializes it with service. Reynolds Zinn is one of the guys who was on the benchmark, one of the early Berkeley guys getting his PhD in this, and an architect at Databricks. And they talked about running, a cloud benchmark with $1.44 per terabyte. Not to buy the terabyte, to run the sort on a terabyte of data. Kind of interesting. We're talking about what's now as opposed to the background where I was talking about relatively standard sort of stuff about sorting. And then there's a Joule-related benchmark, which for reasons I have not been able to figure out, I could ask other people the question, I haven't. There's something called NTO sort. There's a paper called NTO sort that I point to. These should be, if I've done it right, clickable URLs. It explains NTO sort. Worth looking at, it's 2013. It's again a variation of Joule sort. And I have no idea what the NTO stands for. But what I'm emphasizing is that from both a technical and a commercial perspective, the issues on this have not gone away. You really want something that sorts quickly. And the nice thing about using Apache Spark is often you want to sort where it's not inside a database. So emphasis all through the course. We're talking about data management, but it's not all database. A lot of the things that we've been talking about and we'll continue to talk about are things that are important when you have a bunch of data you're managing, whether it's in a database or not. And sorting matters whether you're in a database or not. I will again re-emphasize, for a lot of the stuff we're talking about, you don't really need sorting. Hashing will do fine. An interesting question is when you need sorting versus hashing. When you have an order by, you care about the sorting, unless you already have the data in sorted order. which allows me to be able to go forward, because I'm gonna be telling you, I actually am barely gonna be able to finish in time. I've got 6 minutes and I'm gonna need it. So external sorting is important. Database may devote, a big part of its buffer pool to sorting. We see about trying to minimize disk or SSD or non-volatile RAM things, and you see about the trade-off. Large block size or having shadow blocks costs in terms of the fan out, but pays in terms of not having to, wait to read in things. And in practice, and this is not necessarily always true anymore because the size of data keeps growing bigger and bigger. The term big data, you know what big data means to me? It's called big data if it's bigger than you had originally thought you would ever have to deal with. More volume, more variety, et cetera, et cetera. There are about 5 different V's that people talk about on that, including veracity. It's a lot of different things that are there. But there is another approach to sorting. Remember, in the not too distant past, we talked about B-trees. Well, suppose that you have a clustering index on the data. You know what you can do? You want to be able to retrieve the data in an order that corresponds to maybe the first few columns. Remember, the B tree could be, let's say, the index could be on 5 columns, and you want it sorted by the first 3 columns of the search key inside the index. The first 3 is good enough, as long as it's a first subset. You can go ahead and you can get the data by traversing the leaf pages. Just walk through the leaf pages in order, and it'll be sorted by any subset of the search key of that index. So that's a really good idea if you have a clustering index. Clustering index, because then you only have to touch each page once. What if the B tree is not sorted? Bing, 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 bing. Not such a good idea in practice. If it's clustered, you go down to the left-hand side and you just walk through the leaves in order. You get the data in order, and you only have to touch each page once, so that's kind of good. If the data is there, terrific. If the data isn't there, then you're going to be using the RDs to get the data, but you only touch each page once. Okay, so that's kind of neat. If it's not clustered, then you're going to have to bounce around each time, and if it's 1 IO per record because you got rid of the page, then everything ends up being bad. What's a trick that I told you that can improve this? Hand name answer. What's a better way of doing this than using the unclustered index as described? It takes advantage of the unclustered index. Yep.
Kevin, and you're gonna just scan through using
the index, the leaf pages of the index.
Start at the very
and you get the RIDs.
Get the RID.
And
go that way.
And yeah, but you get the RIDs, you're going to be touching each data page a lot of different times. How to avoid having to touch each page a lot of different times?
You just scan through based off the page, right?
Yeah, but the trouble is that I'm going to be touching each data page a lot of times. Well, here's the thing that you could do, and then let me tell you why, and this was a trap, why it doesn't work. What I can do is I can touch each page once by sorting the RIDs by the page ID. Remember, an RID consists of page ID and flood ID. So if I only want to touch each page once, I can use the unclustered index, and I sort by page ID. What's wrong with doing that? I wanted to produce the data in sorted order. Sorted order means following the order of the leaf pages. By sorting them based on page ID, I only have to touch each page once, but I'm not going to be getting the data in sorted order. I'll be getting it in sorted order based on page ID rather than based on the search key. So trying to go ahead and take advantage of that trick is not really getting it working. So sorting by the RDs by page ID saves pages, but doesn't do what you were asked to do. So it's kind of a bad idea. So again, there are all sorts of great things that you can do. The in-memory, quick sort ends up being a really good way of actually doing things. The amount of work that's been done on sorting is absolutely amazing. Jim Gray went from IBM to Tandem to DEC, where he, using the Alpha chip, ended up proposing some of the sort stuff, because on DEC's Alpha hardware, he had an Alpha sort, which was a winner of some of the sorting things for a while. So he simultaneously did things that were great for the industry and great for the companies that he worked at. And again, if you have a clustered index accessing the data in order based on a subset of the search key, ends up working really, really well. Questions on this? answers on this. Now that I've gone through all the sort of details, you should know how all this stuff works. And one lecture corresponds to one lecture. We were starting to talk about query processing next time. 30 seconds left. You have to prefer. Sorry.